My name is Tulani. I will be presenting our paper titled Helically Wrapped Supercoiled Polymer Artificial Muscles Design, Characterization, and Modeling. Artificial muscles are defined as materials that reversibly change shape under external stimuli. SCPs are a subgroup of robotic artificial muscles that demonstrate large strain and high power density. One of the nice things about SCPs is that they are low cost, accessible, and easy to manufacture. SCPs are made through supercoiling polymer fibers. They can generate significant linear, torsional, and bending contractions. SCPs have been used in preliminary robotic applications like robotic hands, soft robot gripper, and wearable devices. SCPs can be characterized based on their manufacturing method. Non-mandrel SCPs are manufactured by inserting twisting on polymer fibers until they overcoil on themselves. To have a stable structure, these overcoiled fibers are double-bagged to ensure the torque is balanced. Mandrel SCPs, on the other side, are made by coiling fibers on a mandrel. Non-mandrel SCPs are generally heat-treated through joule heating, while mandrel SCPs are heat-treated by using the oven. Their performance is different based on the manufacturing technique used. Non-mandrel SCPs produce between 10 and 20% strain, and mandrel SCPs lift between 10 and 30 grams of load. In the next slides, I will show why this performance is not sufficient for robotic applications. The underlying desire is to obtain actuators that produce large strain and large force. The advantages of mandrel SCPs is that they exhibit large contractions and do not require pretensions. Because we can control the pitch during manufacturing, high strokes can be achieved. Strokes of over 70% are achieved when the pitch is 1 mm. However, the catch is that these strokes are with no load. On top of that, the coils are actually very fragile and exhibit low repeatability. The upside of non-mandrel SCPs is that they exhibit large strains at higher loads. For loads bigger than L2, but before the sharp decrease in strain, the strain performance is the maximum. The big downside of non-mandrel SCPs is that they require pretensions and perform well under constant loading conditions. Because of the manufacturing method, in non-mandrel SCPs, the coils are natively touching, and contraction means distance is limited until the coils are pulled apart by initial load. That means the operation load has to be known in advance. HW-SCP combines advantages of non-mandrel and mandrel SCPs. It is a tunable actuator that has large contractions at low loads and higher forces at higher loads. By changing the pitch, diameter of the mandrel, and fiber diameter during manufacturing, we can alter the performance of HW-SCPs. It turns out by changing from polymer fibers to non-mandrel SCPs for fiber, we can better change the stiffness of HW-SCP, leading to robust coil structure, hence higher repeatability. From this graphic, we can see that HW-SCP eliminate the undesirable behavior of both non-mandrel and mandrel SCPs. Worth noting is that the mandrel SCP is made from the polymer fibers. Their poor performance is believed to be due to the poor stiffness of the fibers. By using non-mandrel SCPs as fibers for HW-SCP, the stiffness can be much better, hence the remarkable improvement in load capacity and durability of the coils. The manufacturing process comprises 4 steps. In the first step, a twist is inserted on nylon fibers until supercoiling. The diameter can be changed by changing the ply number. This assembly is then heat treated through joule heating to form non-Mandel SCPs. This non-Mandel SCP is then used in our custom-made fabricator for coiling. It is in this step that the pitch and the Mandel size can be changed. And the final step is to heat treat in the oven. The temperature and time for heat treating is determined empirically. In our experiment, we use 180 degrees for 1 hour. The thermomechanical properties of the actuator are described by the first equation, where F is the force output, X and XL are the current and resting length of the actuator respectively. K1 is the stiffness, K2 is the damping term, T is the actual temperature of the actuator, and T0 is the ambient temperature. We implement two models for our experiment, the polynomial model and the Prusik hysteresis model. For the polynomial model, PI's are the constants and I is the input. Hysteresis is the behavior where the output depends on whether the input is increasing or decreasing. It is a common nonlinearity in artificial muscles, and the Prusik model has been implemented in literature for SCPs. For this model, Uij is the Prusik weight, while Sij of I is determined by input history. L is the level of discretization, and B0 is a constant offset. We ran two sets of experiments, strain voltage and force voltage. The setups are similar, with both having a fan attached at the top of the actuator. For the strain voltage, we have a magnetic displacement sensor which tracks the displacement change as the voltage is changed. For the force voltage, we have a load cell attached at one end of the actuator. As the voltage changes, the load cell will track the force change. We tested actuators with different Mandel sizes, fiber diameters, and pitches. More details about the configuration of the actuators are in our paper. As expected from literature, the force voltage exhibit linear behavior, while the length voltage is hysteretic. For both sets of experiment, monotonically increasing steps of voltage from 0 to maximum and then decrease to 0. Each step was held for 90 seconds, and the steady state force and strain was obtained by averaging the last 10 to 15 seconds. The Prusik model captures the behavior of the experiment well. Here we show the summary of the results. From figure 1, we see that the strain is higher at low loads. This is likely due to the fact that HW-SCPs resemble Mandel SCPs. Under large loadings, the coils are farther apart, hence HW-SCPs work like non-Mandel SCPs. The strain is also increasing as the Mandel diameter increases. This is likely due to the stiffness change as the inner diameter increases. In figure 2, HW-SCPs with larger fiber diameter generate larger force output. This is due to the fact that the force generated by HW-SCPs are positively correlated to the diameter. In addition, under higher pretensions, HW-SCPs generated higher range of force outputs. In figure 3, the heating and cooling time constants were measured based on force voltage as a metric to quantify the actuation speed. The average time constant for heating and cooling is 5 seconds. The time constant increases slightly as the diameter increases, and we don't quite understand why that is. Current research have shown the need for large compliant deformations with small pretensions, and HW-SCPs show promise towards this front. This means that HW-SCPs can be embedded in soft media and used where large range of motions are required. Additionally, HW-SCPs exhibit faster cooling times, which open doors to be used in higher frequency cases like assistive devices. Thank you so much for listening. If you have any questions, do not hesitate to contact me. Thank you.